Thank you. Go ahead.
All right. Good afternoon, everyone. I'm Tengfei Mo. Along with me is Abin Shahab. We both work at LinkedIn Platform as a Service team. We also have today have Sean, Brian, and me, Joe from Machine Learning Relevance team and SRE team, along with us in the audience. Today, we will talk about experimentations of the Kubeflow at LinkedIn. So I will go through machine learning use cases and our motivations behind Kubernetes and Kubeflow ecosystem. And then Abin will deep dive into 3 internal Kubeflow use cases and our internal integrations into our ecosystem. So at LinkedIn, AI powers many products that we have. It ranges from job recommendations, message smart replies, and learning courses recommendations, and many more. So machine learning solution has to work at LinkedIn scale as we are connecting more than 500 million professionals to make them more productive and successful. Behind that scale, we have multiple data centers plus Azure fabrics, hundreds of thousands of servers, hundreds of petabytes of data, thousands of concurrent machine learning models being served. This is a popular machine learning challenge pictures. I'm sure most of you have seen it before. This was very true for LinkedIn before 2018 when we had fragmented pipeline that requires manual efforts to connect these steps together, which was time consuming and error prone. For example, after model training, machine learning engineers had to manually push the models to different places in our production environment for serving. And also they had to continuously monitor those model health afterwards in an ad hoc way. That's why in late 2017, the company started the ProML initiative to double the effectiveness of machine learning engineers by making the end-to-end machine learning development easy, fast, and automatic. 3 goals for that project. 1, increase the number of products and teams that can leverage the AI technologies. 2, reduce the time needed for model selection, model deployment, etc. 3, make the machine learning engineers focus on finding creative solutions for hard technical problems using LinkedIn's unique and highly structured data. So it has 4 core components: data management for easy feature transformations, sharing, and access; model training and validations; model deployment to deploy different components of a model to different places in production automatically after training with tracking; model monitoring to generate model health metrics and have automatic anomaly detection and issue investigation tooling. So why we are interested in Kubernetes and Kubeflow now? We really like Kubernetes' extensible system architecture and its declarative API, as we are building our unified compute platform where we can mix all these different workloads. Portability is also very important, as we are strategically planning hybrid cloud setup with Azure fabrics. Workload scalability, auto remediation, as well as outstanding community support are great. So for Kubeflow, it provides an end-to-end machine learning solution. Its pieces map nice to our machine learning pillars, such as hyperparameter tuning, different training frameworks, different serving frameworks. In addition, containerized workload could also provide an efficient way to package machine learning workloads so that it's independent of language or compute runtime. It allows our machine learning engineers to do explorations with state-of-art AI technologies very fast. It's easy onboarding and community collaboration are great. So with that being said, We're very interested in incremental adoptions of Kubeflow components and starting with the experimental integration. Now, I will have Abin to give us deep dive on 3 internal use cases as well as its integrations.
Thank you, Tengfei. So this is kind of an architecture of before we started our efforts with hosted notebooks on Jupyter Hub when we got started with Kubeflow in early 2018. So before that, all our ML engineers used to basically spawn up. This is, you can see like a user's desktop there. They're just spawning up their own notebook servers there and talking to HDFS and doing some Spark queries there. They would have to manage their own local disks. They'll have to manage their own kind of software stack that they install there. If they have images, great. They have some ways of sharing, but not really something that we could support at a large scale. So that, because of these reasons, we started thinking of moving to hosted notebooks, and we looked at Jupyter Hub, and around the same time, we were starting to look at Kubeflow. At that time, so Kubeflow was also using this Jupyter Hub in its architecture. So this is our hosted notebooks architecture, and as you can see, we've added a lot of microservices around that lone user's notebook. So what we did was we actually ended up integrating notebooks to our kind of our certificate systems, our authentication systems, our metric systems. So it's a fully integrated experience for the LinkedIn user who wants to use the notebook. So when the user logs in, they are they basically, when they authenticate, they're given a token from a certificate system, and that token can be validated by the Jupyter Hub's Nginx proxy, which also gets a certificate from our certificate system, and that token is used throughout for the user, and so the hub uses that token to kind of spawn a notebook for the user, and then in that notebook, the token is exposed as a secret. Now, when the user can actually do local operations on the notebook at this time, but if they want to kind of talk to our HDFS systems, then again they end up using the kind of the Spark Magic library inside the notebook, and then they basically talk to an Apache Levy service standing in front of our HDFS clusters, which is also using that token to kind of authenticate the user. The other thing that happens here is user can, when the user is using their notebook, their notebooks are always loaded from a shared storage system that we have built. It's backed by Git. So users can share their notebooks among one another. They can review their notebooks, and all that kind of information is always preserved. And that this kind of Git back storage has also kind of dictated the way we've used notebooks and model training, which I'll go to next. Let's see. Okay. So the other point here is that that token I talked about, it's also used basically to talk to HDFS. So there's kind of a traceability of the user's usage from the point they log in all the way to who's using what data. The next step is, okay, model training. So model training at the POC stage, we started playing with the fairing library of Kubeflow. Users really enjoy the experience of being able to launch training experimentally from their notebooks. But here also we've had to add kind of our customizations to take advantage of that Git back storage. we basically expose when Fairing launches a job. So I don't know how familiar you guys are with Fairing, but user annotates their notebook code with kind of Fairing annotations. And then when they run the notebook, it actually launches a training job. So that training job is basically an instruction to the TF operator inside the Kubernetes cluster to kind of launch a TF job, worker, and master. So along with that, we've changed Fairing in a way that it also launches a config map that is so that all these workers now have access to that Gitback storage code that was kind of which was loaded into the notebook. So we end up using the same image that the notebook uses, and we just have the workers use the same image, but the kind of the code from the notebook to launch workers and launch distributed training. Um, the next problem here is at this time, there is no like intermediary service between HDFS and the TF worker. So now the TF workers have to deal with kind of authenticating themselves to our secure HDFS, which means working with two authentication systems. One is Kerberos, and second is Hadoop delegation tokens. Um, so um, so they are kind of fairly different from Kubernetes' authentication model. So we had to build in some integrations with that. So what we do is when the user logs in, there is an init process inside the notebook when they are kind of launching uh, mm, some node or running some notebook. There's a process for them to authenticate or with our certificate service to get Kerberos tokens into the notebook. And then they can now use that Kerberos token to get Hadoop delegation tokens talking with HDFS. So this delegation token now has to be exposed to the Kubernetes cluster as a secret. So that happens next. And then once it's a secret, then we have to kind of instruct when the user launches a job, either through Fairing or some other way, that job has to say, hey, workers, this secret is your dependency. You have to kind of load it up. So once the workers load up that delegation token as a secret, if it's in the, because it's in the workers Kerberos cache, when TensorFlow tries to access an HDFS library or an HDFS file, the HDFS lib will automatically use that Kerberos token or the delegation token. The other problem here is so the delegations tokens would expire. So, oops, sorry, quick, no, too quick. So the delegations tokens expire, and so there's a question of how to renew that. So we had to kind of figure out, okay, we need to have like a trusted renewer in the cluster who will be able to talk to HDFS and renew it on behalf of the workers. So this part, we are still kind of figuring out whether it's some kind of modifications over the TF operator or is it the TF master. Whatever does it has to kind of present itself as a trusted renewer and also kind of revoke the delegation token when the job dies. Okay, so the next challenge we encountered with Kubeflow was this was a basically Mingju who had accompanied us here. He was kind of experimenting with the MPI, running MPI jobs on Kubeflow, Harvard MPI jobs with V100 NVIDIA GPUs. So what in kind of V100 and NVIDIA GPUs, our GPU topology was, as I've explained here in the diagram. So we had GPUs that are kind of talking over PCI with there are two GPUs on one PCI switch and two other GPUs on a different PCI switch. And so there is this kind of GPUs that are on the same PCI switch can talk to each other at a far kind of higher bandwidth because of kind of NVIDIA Direct P2P protocol that they can use. So that's how. So when we actually are running an MPI job, that will be kind of the ideal, where the workers are on the same PCI switch and can talk to each other using kind of taking advantage of that higher bandwidth. But what we noticed then is that it is not this kind of GPU topology is not exposed to either Kubeflow or Kubernetes, and therefore we might end up with the workers, as you can see, spanning the kind of the PCI switch boundaries, and basically then you are incurring additional bandwidth because you're basically doing additional copies of the data, even if it's all on the same node. So we're still kind of looking at it more. We're wondering when we do multi-GPU training, if it's the network bandwidth that will become the bottleneck, and so this will not become an issue. We're not quite sure about this part yet, but we'll be very interested in kind of learning the community's experience with this kind of large GPU, kind of large GPU-centric jobs. The other kind of proof of concept that we're running that is kind of Kubeflow-centric is our kind of model serving. So with model serving, so this is kind of post-model training. So when after models are trained, usually in LinkedIn, they're trained in this workflow tool called Abin. And they get registered to this model registry, and it has a lot of information such as who trained the model, how long did it take, what were the data sets used, what kind of scores does it have, and it has kind of a kind of reference to the features that this models has used. And then the user or the model author can decide that this model meets the requirements, and they can kind of publish it to our model artifact store. And then from then on, there's a model deployer that can pick it up and kind of stage it and then move it through like our staging and production pipelines. Most of LinkedIn models are deployed alongside the production service. So this is kind of different from many companies where the models are deployed in a separate model serving cluster. We're kind of on the other side because of latency reasons, how our kind of model ML stack have evolved. We've always kind of started with kind of in-memory library-based models that are alongside the production service. But now we're experimenting with this kind of, and we've kind of separated that out, a separate component beside our production service that can kind of load a model at runtime and unload it, and also can make network calls out in case the model is not co-located. So what our work with Kubeflow serving here is that our model deployer is going to kind of deploy a model to the Kubeflow serving cluster, and then it will signal the model runtime environment that that model is ready to kind of be loaded or kind of be counted as something that can be used by the production service. So then the model runtime environment now can unload the previously loaded model and load this one, and which means in this case is basically just being able to call it when the production service needs to call it. Yeah, and then the Kubeflow serving cluster, we've had to make some changes to the traditional kind of TF serving deployment here. We've decided to start with kind of host networking for our model serving, just to kind of get around any kind of overlay network related issues. So when models get deployed there, they have to kind of negotiate with our port registry to make sure they have a unique port, and also our kind of internal load balancers to make sure that the load balancers know where the models are all deployed, and that it gets updated when, say, Kubernetes decides to kind of remove a pod or relocate a pod. So that's what's going on today. What we have planned for the future is we want to kind of add some of the features that we are currently use and love in Yarn stack. For example, we use Yarn's queuing features fairly extensively. Specifically like hierarchical queuing is used across our ML orgs. So we're looking at like how to figure out how to use that in the Kubernetes Kubeflow world. We are interested in using Kubeflow on Azure. As Tengfei mentioned, like our Kubernetes and Kubeflow are an important part in our unified and pluggable compute platform as we move on to that. And the other thing kind of related to queuing is that we want to understand Kubernetes's kind of limits in uh, resource utilization related issues. For example, if it cannot oversubscribe, how does it work with elasticity of jobs and things like that? So we're exploring those things. Thank you.
Thank you so much.